Hello everyone, today I'm going to talk about the principle of Japanese bullet train, also known as the Shinkansen. Firstly, I'm going to tell you a little bit about what is a bullet train, and then I'm going to address an issue that the bullet train used to have and how physics helps solve it. And finally, I'm going to introduce a little bit about a new technology that is applied on bullet train, which is the maglev technology, also known as the Chuo Shinkansen. Bullet train is referred to Japan's high-speed railway lines. It was first proposed in the early 1900s in America and Europe, but only in the 1960s it was officially operated in Japan. Right now it's operated in about 20 countries in Europe and Asia, and its top speed recorded was at 320 kilometers per hour or about 200 miles per hour. This is some more of the recorded speed over the years for the Japanese bullet trains. As you can see, it went from 120 miles per hour at first, and it's around, right now I think it's almost at like 300 miles per hour already. An issue that the bullet train in Japan came across back then was that since it was going at such a high speed, especially when it's going out of a tunnel, it created a very loud noise that can be heard from like hundreds of meters away. And since the Japanese very value their quiet, the Japanese engineer actually came up with a solution for this problem, and they actually take the inspiration from nature, or more specifically from the kingfishers. The kingfishers are very famously known for their fishing skills, in a way that their beak is shaped so perfectly for the minimal splash and wave, so that when they go into the water, there's so little movement that the fish didn't even know that the kingfisher is going for them, and that's how they are so efficiently catching the fish. The Japanese engineers take this inspiration and model the bullet train like the kingfishers beak, and they find out that it produced 30% less air pressure, used 15% less electricity, and are 10% faster. So from chapter 5 that we learn about friction force, we are given these equations, F equal constant times speed, with K and D are constant that depends on the shape and size of the body on the density of air. Now we know more specifically that for the drag force, Fd is equal to negative 1/2 times fluid density times speed of the object relative to fluid squared times the coefficient of drag times the frontal area of the object that is pushing through the fluid. So as you can see, with the very high speed, we're gonna have to have a very small frontal area, very small coefficient of drag, which really depends on frontal area and the shape of the object. So as you can see here, when the object is very round and very less angular, and the frontal area very small, the drag coefficient is very small too. Lastly, I'm gonna talk about what's new in the bullet train. So the first patent is actually back in the early 1900s, but not until very recently that Japan started the construction, and right now only 3 countries have them in operation, which is Japan, South Korea, and China. Right now only a handful of countries that have actually started construction in Europe and in Asia. This maglev bullet train uses a magnetic levitation technology, which is they use magnet to levitate the train, so the only moving part is the train itself. So it creates very little or maybe non-existent friction, so it's very less bumpy, and it can go very fast without being held back by friction of the track or because of the bullet nose held back by the wind. The top speed recorded was at around 600 kilometers per hour or about 370 miles per hour. Here are my references that I used to create these slides, and note that in my research paper I actually only mentioned the physics part of how the frontal area shape and the coefficient and the kingfishers, but I don't really mention the bullet train or the maglev train itself, so I don't really have sources for that, but you can totally Google them online. The maglev technology will actually be taught in physics 4B, so if you're very interested in that technology, then guarantee that you can learn it up there. Thank you for listening.